for joining in. So welcome. Let me see. Yes.
Yeah.
My talk is about natural language processing, NLP, for music information technology. So I'm going to talk about both audio from the music audio part and also beyond music, in general, the audio. So I work for Bose. We are a private company specializing in consumer electronics and audio, and we're owned by MIT. So let's see. Yeah, so just a little bit of history of this talk. So we first created this talk while I was at the MTG at UPF with Sergio and Luis there. And we first gave it at the Izmir 2016 conference as a half-day tutorial. And since then, I have individually given this different versions of this talk at several other places. So this will be the 6th time that I'm giving this talk. Of course, each time it really evolves a lot. So it is a lot different from the original, if you check it out. Okay, so I work in a field called music information retrieval, or MIR. So a lot of times people ask me, what is MIR? I would simply put, I would say that it's AI for music. And if we go kind of broaden a little bit beyond music to the general audio, then I have what we call audio or sound AI, which is to understand the world through analyzing the audio and the sound in your surroundings. So what exactly is MIR? I would say that it's a set of technologies that enable machines to understand and produce music like humans. For instance, Google has a machine perception team that and they have a project called Magenta, which focuses on a lot of AI projects for arts and music. So one of them, maybe you have seen it this year in April, Johann Sebastian Bach's birthday, and they put out this doodle, which actually, given a random melody, it can automatically harmonize the melody in a Bach chorale style, so that it actually sounds very sophisticated. And you can check out the paper. It's called The Counterpoint by Convolution, also a very smart title. Another example, audio fingerprinting or order marking allows you to recognize, basically, if you hear a sound in the radio when you're out and you're not sure what's the name of the song, right? You pull out your Shazam and then it instantly recognizes the sound by detecting a special signature that was injected into the audio. Spotify does music recommendation, as also does Pandora. A better understanding from the music information retrieval would allow these recommendation engines to better recommend music. Right? So there's a lot on the plate for music information retrieval. If you're interested, you can check out the Izmir International Society for Music Information Retrieval Conference. Really a very vibrant conference, the annual conference. A lot of interesting technology there. So yeah, as I was saying, going beyond the music part, we're going to what we call audio AI. So actually, this is a part of the research that I have been focusing on in recent times. Next month, there's a UK's workshop, the detection and the classification of acoustic scenes and events. This workshop focuses on a lot of the audio AI tasks, such as acoustic scene detection, audio event detection and sound localization. So imagine if you're at home, I mean, if you have an Alexa at home and you are not at home, Alexa could listen for the sound of glass breaking, right? So that maybe can alert you that someone has broken into your house. So there are already companies that focus on audio event detection, such as Audio Analytic. Yeah, so natural language processing. I believe that most people in this community of AI and deep learning are no strangers to NLP. NLP is really one of the cornerstones of modern consumer-facing AI. Basically aims to enable machines to process and analyze human language data, often in very large quantities, and includes some of these classic tasks such as sentiment analysis, machine translation, information retrieval, question answering. One of the interesting things of NLP is that there's a lot of specialized domains that you can see. If you go to one of the top conferences, you can see workshops focusing on NLP for legal processing, legal document processing. You can see for medical NLP, or even this year there's a workshop that focuses on e-commerce NLP at the WWW conference. Typically, you don't see music there, which is actually why we are working on a new workshop right now to bring it to one of the top conferences. So that might change later this year. What I really want to focus on in the talk at the summit would be the NLP for MIR and audio AI, right? So I'm going to give some examples here to kind of illustrate the use of NLP in music IR. For instance, I think one of the major motivations for the modern NLP is really to leverage the vast amount of information online. Those information, usually they are unstructured texts generated by a human being. So how to leverage those large quantities of unstructured text and turn them into structured text, structured data, I think is one of the main use cases, which also applies in this case. So for instance, in the music domain, we might be interested in the large quantity of articles, texts written online about artists, about music, or maybe even users, listeners talking about music. There's a lot of rich information there, and we might apply some NLP processing techniques such as name entity recognition, entity disambiguation, and entity linking. So entity linking, in that final step, you really link the entity in the text into a knowledge base with a specific URL. So this entity is pointing to that specific Wikipedia article, for instance. In that way, you have turned unstructured information into structured data. And from there, you can also do more, like in this case, relation extraction. That's one thing. It could be a restricted set of relation, or it could be open information extraction. And from there, we can even build knowledge bases that are knowledge graphs that are specializing in the kind of music content knowledge. On the other hand, we can also leverage multimodal data. So for instance, in this case, we have mapped Amazon reviews of the music albums. So those data and million sound data set, which provides audio features, and Music Brains, which offers the music metadata in the semantic web. So if we align those knowledge bases and data and merge those, we created the multimodal music data set called Mu, and we use that to do a multimodal deep learning for instance, for music genre recognition, right? So it really leverages all the different modalities. So going beyond music again, we're going to the general audio domain. We have the audio AI. There are really a lot of developments recently on audio AI. I'm going to talk about one of them, which is the audio event detection. So in particular, in the talk, I will talk about the data sources, such as audio set and free sound, and the metadata that came with it, such as the ontology for audio, which actually was formed by using some of the text mining techniques. And then pre-trained DNN models, such as the VGG-ish model that's commonly used in the current audio deep learning, and also the some of these category competitions that came out of it. Yeah, one particular thing I think is interesting, actually, this year at NACO, we see a paper on audio captioning. So, in which case, if a microphone is picking up the audio events from your surroundings, usually returns these discrete labels such as a vehicle or speech or being outside. But what if we can turn that into a natural language sentence using the NLP techniques, so such as in this case a muffled rumble with men and women talking in the background while a siren blares in the distance. So I think that really has some very interesting applications. So that is the gist of it. So to wrap up, I have several, I think, trends that I want to share. So I have been working in the machine learning, in NLP, and in audio for the past years. And I made some observations, which I want to share in the talk. So I think the themes are grouped into these four different streams. Common app architectures for domain-specific designs, which just means that if you're applying a CAN in NLP versus in audio, they're going to be different, right? How they're going to be different to be more efficient. Second one is data source and legal concerns in audio research. Either in music or in audio, copyright, privacy, they're all very important topics. So deep learning narrows gaps between disciplines. Basically, what we see is that traditionally what took years of training in specialized domains, such as digital signal processing, these days with DSP or computational linguistics, these days, really you see that with the deep learning, you can quickly adapt to different domains and different tasks without a lot of deep specialized knowledges. And finally, the era of transfer learning. Here are a few slides that are kind of previews. So yeah, for the first one, right, common architectures of domain-specific designs. Here I'm specifically talking about using CNNs for audio and how it differs from like using it for image and for text in the filter sizes, filter shapes. And acoustic brains is one effort that we had at the MTG in UPF to address the data sharing problem for music research. And finally, the transfer learning, the era of transfer learning really in the image domain and in audio domain, I think is pretty established for a while. But in NLP, I think it took a little longer to figure out, for instance, what is the right pre-training tasks for the effectively fine-tuning, right? And a lot of these interesting questions, which actually only last year people are saying that, oh, really, era of transfer learning, we can say that for NLP, it is now here. People have really figured out how. I'm going to give an overview of all these different domains and how the commonalities and differences, right? So in the end, I think just one quick slide the future of audio-centric multimodal smart devices, a initiative that Bose is currently launching, which is the Bose augmented reality, Bose AR. And I'm going to just briefly describe it and the SDK that is associated with it, so people can, if you are interested, you can check it out, and you can develop new experiences, AR experiences with the Bose AR. And that's my talk today. Thank you.
I'll be talking a bit of a preview about some of the work that Ericsson is doing in terms of building tools for doing anomaly detection and other sorts of AI data science based monitoring tools for software infrastructure. So at Ericsson, we actually do quite a bit of machine learning. You might have first heard of Ericsson from the Sony Ericsson phones that were being made over 10 years ago. Right now, Ericsson does most of its work in building the infrastructure for cell phones themselves. So a lot of the cell phone towers and cell phone networks. And so we're involved with basically everything, a lot of the stuff that happens at the back end. So building up those networks, doing and helping providers manage and run all of those networks. And all of that actually involves quite a bit of data science. So the organization that I'm a part of, the Global AI Accelerator within Ericsson, works with all these different areas and doing things like anomaly detection, reinforcement learning, deep learning, predictive machine learning, and developing secure machine learning platforms to do all this so that we can do all this data science in a secure way that doesn't invade on privacy or regulations. And the specific example that I'll be talking about in my talk is software infrastructure for these business support systems. And in general, many of these concepts will apply to any piece of software that you have running. So it could be, I don't know, like Spotify's tool or some other apps. In general, basically any app that's running in some distributed way. Our specific example is the tools that are being used for managing customer orders for cell phones. So this software, it runs on hundreds of servers, hundreds of APIs, and on each of these servers, there may be hundreds of metrics that are measured. So things like the CPU levels, memory levels, and other measures of network traffic. And basically what that means is whenever problems start occurring, when servers crash or some other bugs start occurring, the support engineers and software reliability engineers can get pretty quickly overwhelmed by this massive amount of data that is getting fit in. So having some data science-based monitoring solutions that can help them more intelligently understand this massive amount of data coming in can greatly improve their efficiency of these systems, the reliability, and make the jobs of the support engineers much easier. So what we've been exploring is developing a data science-based monitoring strategy to help these support engineers do their work. So we've been exploring building things like adaptive anomaly detection systems that can easily integrate into existing systems, whatever their actual underlying details are, and be scalable to large, complex infrastructures. We've also been exploring building tools for doing automatic root cause analysis. So, for example, when some API our tool can act as a sort of recommendation system and suggest the potential root causes. So maybe something like this machine is starting to have really high memory levels, and these processes are slowing things down a lot. And all of this basically leads to enhanced infrastructure management, where you can use data science tools to more quickly diagnose system failures more quickly resolve incidents and improve compliance with service level agreements. And we've even been starting to explore things like using machine learning based tools to predict service availability some amount ahead of time and forecast the system health levels in the future. So use the machine learning tools to basically understand that underlying footprint in the system and start to see when things are start misbehaving before they actually occur. So in the process of doing this, we've had to clear up some hype and misconceptions about what exactly machine learning data science isn't capable of. So I mean, ideally what we'd want in an anomaly detection system is something that can automatically detect dangerous changes, predict failures many hours ahead of time, provide easy to understand root cause analysis with perfect accuracy and limited data. And of course, all of this is almost impossible. There's always some catch and some limitations over what we can do. So it was important to clarify that anomaly detectors in general can't provide definitive yes or no answers. They only output probabilities of how likely an error will occur. They can't provide definite root cause analysis, only suggestions about potential root causes based on correlation. They can't entirely replace human judgment and experience. We'll always need some domain experts, some human experts around to evaluate the performance and catch problems that the machine learning algorithms can't detect. And in general, these anomaly detection systems have to be tuned to some extent for different systems, metrics, time ranges, and frequencies. And even if everything works perfectly, there will always be something that's unpredictable where the method will fail. So going back to replacing human judgment, we always need some support engineers. So one tool that we build is some tools for automating root cause analysis. And we had some, because of time constraints, we always work with limited domain knowledge. So the support engineers that we're working with, their highest priority is always fixing the problems that are coming at them. So we can only get a bit of their time once in a while. And ideally, we'd like all of our data to be labeled, but in practice, that's limited as well. So we developed the solution that minimizes the amount of that's needed, and that's basically just estimating the most probable root causes based on the most correlated behavior. So looking at the time series that's tracking some of these spikes in something like the API response time and correlating that time series behavior back to other time series. So let's say this API spiked at 10 a.m. at the same time we saw an API spike, a spike in the CPU usage on this server. So then we can suggest that that server was a potential cause of this issue, and then that gives the support engineers a clear route of which devices metrics to investigate first. So, and another important thing that we discovered is that when you're deploying in the machine learning in the real world, there's always all these things, the extra steps we have to do that the clients and users aren't often aware of. So what we often see is that predictive machine learning models initially work well upon deployment, but then start degrading after several months. And this can happen for reasons that are entirely out of the control of the machine learning engineers. And a basic step to this that another speaker working with 10 points we get to, you basically can build tools to do data monitoring and alerting. So like making sure that the data schema stays consistent, that the tracking changes in the statistical distribution of features, and building tools to monitor this performance so that the retraining of the models can be triggered and the appropriate alerts can be sent for engineers to look into. And some potential causes of this type of machine learning performance degradation are things like concept drift and feature drift, which I'll delve into more technical details during the talk. But that basically has to do with drift in the underlying statistical distributions of the data. There could be systematic changes to the data pipeline where, say, some new feature might start to be created, or some categorical feature might start to have new values, or even something might get outdated in the databases and no longer be updated. The actual interpretation of the predictions been changed. So if the machine learning models, say, making lots of false positives, the users of the machine learning model might start to ignore and behave with it in different ways. And there may be other biases exist, and in general, there are always just random statistical fluctuations that can occur. Yeah, so that's the quick preview of my talk. I'll go into all of these into a lot more technical details next week.
Thank you. Again, this is Anurag Wakhlu. Just a little bit about myself. I've spent about 25 years in financial services and technology. I currently work as a business consultant at Dassault Systems, which is a French firm that spans actually 11 different industries that they operate in. I work for the financial services industry. Before this, I was a portfolio strategist at State Street Global Advisors. And prior to that, I was at Fidelity on the trading system side. So I've spent, I'm a technologist by heart and a business person by head, as I like to say. And I've also spent a lot of time in machine learning for financial services and a few other supply chain and other topics. A lot of those different topics interest me. So my presentation on October 1st is going to be about data science for business. It's not a technical presentation. It's more around, what is this thing? Everybody hears a lot about it. There's a lot of buzz around it. There's a lot of hype around it. Every sort of new fintech startup seems to be doing something with data science, AI, ML. So this is more for sort of non-technical people. Obviously, the other ones obviously know a lot about this stuff. To understand what is data science, how did we get here? What are the big underlying trends that got us to this point? What is happening in this space from a end consumer, end user, enterprise business perspective, and a few things on where this can go in the future. So that's sort of the overall summary of what I'm going to be eventually presenting next week. This lady, as you mentioned here, is Sophia, which is the most advanced humanoid or robot right now, which is AI based, and we'll look at some of this in more detail. So I'm going to run through a couple of slides very quickly. I know we are a little bit short on time as well. How much time do we have? 10 minutes at this point, or is it less than that?
Time.
Okay.
You have easily 10 minutes, 15 minutes.
Easily 10 minutes. Okay, perfect. So,
yeah.
All right. So
we'll.
Sure. Okay, thank you. So I'll talk a little bit about what data science is. Again, this is the preview of what we're going to see in a week from now. But what does it mean? What is the data scientist? What do data scientists do? And it's all about getting relevant insights from data. And obviously, we look at how AI and machine learning and those things fit in. But as you can see on the screen, data science is sort of a multi-domain. It spans many different areas between scientific method, visualization, mathematics, statistics. That's a lot of that comes together under the very broad umbrella of data science. So the idea is to figure out, okay, what is this thing? What do we do in data science? So this is the part that, there's all of these technical terms that you see on this black box in the center. This is not the part I'm going to be talking about in detail. So that's why I put the little, astonished kid on there. This is what you do in data science as one of the many sort of core technical aspects of data science. And What we'll talk about instead is what is this used for, right? So what do you do with the, classification? What do you do with image recognition? What do you do with all of those things that I showed you in the earlier slide on the black box? What do you do with them? And what you do with them in the business context is things like these on the screen. You do fraud detection in financial services. So you do anomaly detection, which is the underlying part of fraud detection, for example, for figuring out, if somebody has swiped your credit card at a gas station for $1, is that you, or is that somebody who's just stolen your credit card at a restaurant? Things like that. We're going to look at how some of this applies, or more like use cases. It's not, how do you go from that underlying technology to this thing in Netflix? If you watch this, you will also like to watch something else, recommendations, those kinds of things. What are the business applications of the underlying data science methods and AI and that kind of, those kinds of technologies? Customer sentiment analysis, a big chunk of what we do with data science today is in the space of customer experience enhancement. Obviously, it's being used across many, many, many different industries. I think personally, no industry is untouched by data science. No industry will or is untouched by AI and everything else that comes with it. So then we'll go a little bit into how do we get there. And the idea behind this part of the presentation is for us to understand the larger trends that got us to this point. The three big trends, just to enumerate them, are the global connectivity that started about 2.5 decades, late 80s, early 90s, when things started getting connected across the world. That connectivity and the resulting amount of data that started getting generated much later by devices that got connected, smart devices that got connected. IoT obviously is Internet of Things, IoE, which is Internet of Everything. Now, pretty much everything we look around, anything that has a chip in it is getting smarter, and even better. And they're connected and they talk to each other and they generate gobs and gobs of data. So the reason to understand some of these underlying trends is for CXOs, for example, who might be attending, or even startups, all the way from startups to enterprise startups to CXOs. Why did we get there? Where is this going? Where are the opportunities? So this part of my presentation will cover, what's happening in this space, what's predicted, or no pun intended, what's going to come in this space in the next 5 to 10 to 15 years. So that if there's opportunities there, you can capitalize on them. So again, the business use of the underlying technologies and trends. A lot of you might have seen this, what happens in an internet minute. This is just to give you a sense of how much data is produced all the time in this world. 1.7 megabytes of new information created per second per person by next year. 90% of the world's data was created in the last 2 years. That's how much data is being created. So data is a second big trend that sort of came about piggybacking on the back of connectivity. We create data when we have, smart watches, smartphones, when we tweet, when we send pictures, upload, likes, when we go jogging, kayaking, running, swimming, and all of these activities. Every single one of these produces data. A modern day jetliner like a Boeing 787 produces 40 terabytes of data per hour of flight, for example. Just imagine 40 terabytes of data. What is it used for? All this data a lot of this data is fed for system analysis. A lot of this data is used. Sorry, I'm getting a lot of disturbance on the call. Okay, a lot of this data is used for feeding into digital twins. Why do you feed into digital twin? So you can do a predictive maintenance of an engine. So you have a real engine fitted on a 787 Dreamliner, and you have a digital twin of that sitting in, the lab of the company that owns the thing, or could be sitting at GE. And GE's business model is, hey, we will give you this engine. We will do predictive maintenance on this engine so we can ship you the part as soon as we think it's going to break down or wear out, right? So that's the business model that can come out, or has actually come out of something like creating a digital twin for and leveraging AI and machine learning to do predictive maintenance. Obviously, again, you're using that 40 terabytes or a big chunk of that data. Our financial markets, NASDAQ, OMX, NICE, global exchanges around the world, blockchain, not blockchains, cryptocurrency exchanges, Bitcoin exchanges, all of these, just options data, for example, with the 80 global marketplaces that we have in the world, just the options and equity derivative data is 2 petabytes of data just around that. So a lot of data is being generated constantly in the world, right? And we'll go a little bit more into that in the actual presentation next week. The third big trend is compute power. As you can see on this graph here, 2 key things to note. One, this is a logarithmic scale. So that red arrow that you're seeing going up, if it was a normal scale, would be like a hockey stick almost. But this is a log scale. Each level is 10x a multiplier than the previous level. Where are we today? This green line around 2019, just hitting 2020. So we just recently compared to this x-axis, which goes back to 1900, just recently in 2015, our compute power exceeded that of a mouse in 2015. By 2023, we expect the compute power to exceed that of a human brain. And another key thing here is in each hour, the amount we are processing now exceeds what we did in the previous 90 years of computation. The amount, so the point is the mind-boggling amount of compute power and computation that is now available. And that is the third largest trend: connectivity, data, and compute power. And that's how we have gotten to where we are today with AI. Just to give you another example, the Apollo guidance computer is the equivalent in power of your Nintendo Entertainment System, version 2, not even the new one. The Cray 2 supercomputer had the compute power of an iPhone 4. iPhone 4. We're at iPhone 11 now. So imagine the compute power that you have in your hands today, in your devices, in your watches, in those small, smart IoT devices. So those are the trends. Then the third part of the talk will be a little bit about, what can you do with this, primarily in financial services. There's obviously many applications across every industry in the world today. But what can you do with this primarily in financial services? Just to give you examples, Data Miner, which got famous for predicting a major drop in, I believe, Apple stock 3 seconds before the stock actually dropped. 3 seconds is lifetime in financial services. You could make a lot of money trading in that 3 seconds. But they analyzed the billions of tweets they drink right from the Twitter fire hose to predict stock movements. More than half of the hedge funds use AI machine learning for investing. The big financial services firms out there, BlackRock, JP Morgan Chase, are using AI for investing and for customer experience, and obviously for algorithmic trading. Robo-advising, this is another, everybody's going to passive investment. The assets in passive investment, I believe, just about 1 or 2 weeks ago, have crossed half of the assets between active and passive. That is a massive shift in how people are investing. It affects active managers directly. Margins are getting squeezed. There's fee compression. You can buy the S&P index now for 0 basis points pretty much. How are you going to make money as an asset manager with a 0 basis point fund? Where are you going to make money from? So, and now as more of the world, thanks to the 11-year bull market, is moving to passive management, which can be done, lo and behold, by machines, what happens to this industry? As one example, right? Disruption, massive amounts of disruption. And I think, and that's my prediction, a machine managed portfolio will outperform a human managed portfolio in 7 years. And 7 years because I made that prediction 3 years ago, and I used to say 10 years. So the level of AI that we are seeing now will make this data-driven approach to investing. Computers are much better at doing data and analytics than humans are. We have built machines that are in many ways, obviously much faster than us, but also getting much smarter. I'll take a few examples of things that I have done personally over the last few years, more recent examples. This is a three-dimensional risk heat map that I built, which was predicting, you can see on the y-axis is the volatility of bond yields, for example, equities, volatility, currencies, and a few commodities. And one of the machine learning things I built was being able to predict with an average of 70% accuracy to predict the 1 month forward volatility in those 15 global macro indices, which you can use for portfolio construction, portfolio management, risk management, insurance. You can use this across financial services. And 70% accuracy is pretty good in financial terms. So we can talk a little bit about that. And then the last part of the presentation will go into, what does the future look like? Again, where are these trends taking us? And I'll speak a little bit about that. Predictive shipping. Amazon.com, I believe, has filed a patent on some parts of this, is, what they think you want using machine learning, AI, and all those data science techniques to ship you things before even you want them, or that you need them, And it's going to come from not on a truck like that has to be driven by a driver. It's either going to be a autonomous driving vehicle, or it's going to be one of these guys that flies down from the sky, right? Many of you might have heard about deep fakes. Using that same AI technology, you can create deep fakes, as they're called. You can make pretty much anybody say anything in such a realistic way that the human mind can't figure out that this is a fake or not. And if you Google deep fakes and look at YouTube, you'll see countless examples of, they've made celebrities say things with very, very photorealistic lip movements and facial expressions that you just can't imagine that this was done by AI. But from deep fakes to fake news. Another example, OpenAI, which is a San Francisco-based company, they fed, and this made news a couple of months ago, I think, they fed the first half of the first sentence. Russia has declared war on the United States after Donald Trump accidentally ... That's what they fed into this model, that AI model that they created, and the AI model wrote the rest of that news. And you can read it at leisure. If you Google OpenAI and fake news, you'll probably come up with this example. That's how good machines have become. So imagine what you could do with this technology, good or bad. It's amazing. Some of you might have heard of AlphaGo and AlphaGo Zero. I'll talk a little bit about that. But the fact that AlphaGo could learn by observing or by learning from 30 million moves of expert human play, defeated the reigning Go champion. By the way, for those who don't know, chess obviously is a game of strategy, and it has 10 to the power, some number of moves, I think 80 or something, if I remember correctly. Go has 10 to the power 170 moves. To put that in context, the number of atoms in the universe, I believe, is 10 to the power 80 or 90. So Go is considered to be a much, much more complex game. And we humans pride ourselves on our intelligence. That's our final frontier. AlphaGo observed 30 million moves, learned the game, defeated the reigning Go champion, defeated the reigning human Go champion. But then the icing on the cake, and I'm going to talk about that in the actual talk, is somebody defeated AlphaGo as well. Some of you might have seen this video. Google makes a phone call. It blew me away, honestly. When I saw the video, the level of natural conversation, NLP, natural language processing, which is another huge part of data science. It's all in the same connected field. And they gave an example of this. It was a demo, but it just shows you where this technology is going and what it's capable of. And I'm going to leave you with the last one, which you can see on my screen. I'll tell you what this is. And there's actually a prize for guessing what this is in my actual talk. So I'll stop with that. I hope I've been on time. Thank you for listening, and